So I just started the video. We've been doing potential energy, and we started with the cat having gravitational potential energy, and she's going to pounce on her little friend. And you can store energy in an elastic and something stretchy, or in chemical like a battery or gasoline or food, or in electricity if you store charge somewhere. And the same amount of work that it takes to store the energy is the same as the amount of potential energy that's stored in it. Kind of makes sense. So how would you calculate the work that she has done in order to lift this weight off the ground? Prez is pointing over there. Work equals what?
Force times distance.
Good. Force times distance. This is very important though. What type of force?
Applied.
Good. Good job, Anna. This is applied force. So it's not the net force. As she lifts it, the net force might be 0. Right? She might be lifting with a constant velocity. What would the applied force be that she has to use to lift the mass?
The mass times 9.8.
Good, so it's mg, right? So our force is mg, and the distance that she moves the mass is the same as the height that the thing gains, right? We say that this is potential energy. So that formula is up on the wall there.
And that's for gravitational.
That's correct. This only works for gravitational potential energy. We use it a lot because it's nice and constant, and we always have gravity around, so it's nice to use. So we learn a lot about gravitational potential energy. So if you're Wile E. Coyote, do you guys know Wile E. Coyote? Have you ever seen? Yeah? I always wanted him to catch the Roadrunner just one time.
He does at the end.
Really?
Yeah.
I've never seen that
You should
before.
watch it.
No, I don't want to watch it. Okay.
It's gonna ruin the chalk.
He always gets some rock that falls off a cliff and smashes him. So this rock is up there. It has potential energy relative to the ground. So when it falls, it will do work, smash whatever's underneath, right? Because it has that energy stored. So this is the formula for potential energy. And this is supposed to be a P here. That's for potential, or sorry, yeah, that's for potential, and this is for energy. And so if you know the mass and the height, you can calculate not only the work that it took to get it there, but also the potential energy that is stored there. How would you prove, if I picked something up, how do you prove that there is potential energy stored in this?
You transfer.
You get the same amount of energy out when you drop it. That comes next. Yes, Jude?
How would you calculate potential energy in a horizontal thing? Like, could you use D interchangeably with H?
No. So that would be a different kind of potential energy. Like my waffle, it's sitting on the counter.
You like split it across.
It has chemical potential energy, but it doesn't have gravitational potential. I mean, it does, but only affecting. Yeah, the horizontal thing, you're gonna have to use some other form of energy to move it against friction. So you're gonna have to apply a force, or use an elastic, or drive it with a motor, or something like that.
So it's kind of just like the FDF formula.
It's FAD, like the work to move it is still FAD, but it's not this because it's not going up or down.
Okay, sure.
So that's a good question. If you see a problem where it's moving horizontally, it's not being raised or not falling, then you cannot use this formula for that. It's a different type of energy. Okay. Some of you should be asking the question, okay, great, Mr. E. I take 1 kilo and I raise it up 1 meter. You can tell me the potential energy I have here, right? Let's say this was 1 kilogram and I raised it up 1 meter. How much energy is here?
10.
Close to 10, right?
Yes.
9.8. So M is 1, G is 9.8, H is 1. So this should have 9.8 joules of energy, yes? If I drop it, what does it have now? 0. But if I push it off the table, it's still false. If I dig a hole underneath you, what are you gonna do? You're gonna fall, right? So just keep in mind that this MGH thing, it's just relative to a certain place, okay? So answer those 2 questions, if you would. Jot those down.
And 17, 118.
How high is it in the beginning?
0. Oh, you have to do a minus sign.
For the first is 0.2.
So the table is 1.2, right? And then we lift the object up 0.8. So relative to the table, your height is just 0.8. Yeah. So relative to the table, the thing has 130 or something? 120? Really?
170.
80 and
118.
okay, 120. We'll say 120 joules. Okay, now that's with respect to the table, because we lifted it up 8 centimeters. But what about relative to the floor? Now we gotta add them up. So it's still 15 kilograms, it's still 9.8. But now it's gonna be 2 meters, right? So this is gonna be like 300 or so?
Yeah.
294? Okay, so I don't understand. How can it have 2 different potential energies? Who can explain this?
Different heights.
Okay, different heights, good. Sam?
Is the potential in 2 different types of energy?
Is it 2 different types of energy or same type?
Same
type.
Okay, same type, but that's a good question. So we're just lifting the thing up, we're doing the same amount of work. How come we're getting 2 different values for energy movement?
Because of the table? Like,
Yeah, I think so. What you're saying is relative to the table, so if you just start at the table and measure to the top, you have 120 joules. But if you start at the floor and you go all the way up, then you have 294 or whatever we got. It's going to be more. Okay, so then your question should be, who decides where 0 is? Like, who decides where you start?
Whoever makes the question.
Put your hand in the air, your finger, point it like this. That's who decides. You decide.
Oh,
Because you're applying the force.
Because you want to decide, you can decide where you want to find the energy relative to. Okay, so if you want to know the energy relative to the table, you make the table 0. If you want to find the energy relative to the floor, you make the floor 0. And you can change where 0 is depending on the problem that you want to solve. Now in grade 12, if I'm teaching you, I will teach you how to find your total potential energy relative to the whole Earth. But we're not going to do that this year. We're just going to do the difference in potential energy. So that's really what you're finding. If you pick something up off of a table, you're really finding the difference in potential energy from the table to where you lift it. Make sense? Okay. Turn to the person beside you and explain what I just said. Yo. I will, I'll get you some. I gotta go to the office and do some photocopying anyway, so I'll grab you a roll. I don't think I have a roll right now. Yeah, sure. Yes, go.
Is the lesson done?
No, not quite.
That is so rough.
What?
We had to take the other test first period of first day. We were the first class, and we have to take the midterm first day of first class.
Are you gonna take the midterm? First block of the day? That is not fair.
And it's like on the 12th.
I'm sorry about that. You good? So, to summarize, you're finding when you do the MGH, you're finding the difference between one place and another. Just so you're aware. Okay, try to do this one. Oh, and you got a question? Yes, you'll get your test back. I'm doing this quick. And then, well, trying to do it quickly. Okay, so is this MGH? No, because you're just pulling sideways. There's no gravity involved. It's got to be work, Ollie. Nice job. Let's have a golf clap for Ollie. So, as Ollie aptly pointed out, the work you do to... Oh, I have one of these. The work you do to stretch your bow and arrow. Valentine's Day, Cupid. The work you do to stretch the bow is the same as the potential energy stored in the string. Okay, so if you find the work it takes to pull it back, you will also know the potential energy stored in it. So we can say the work is equal to the potential energy stored, so that should be force applied times the distance. And we go 12 newtons times 0.2 meters. 2.4 sounds right to me. And that'll be in joules. Does that make sense? Yeah, the work you do is the same amount as the energy you will store. Weird, right?
Also equal to kinetic energy.
Yeah, so when you release the bow, will you be able to solve for the kinetic energy of the arrow coming out?
Probably.
Yeah, it'll be the same.
So the difference between those two formulas is that the first one is for like this, like the work, and then the what was the second one again? The gravity.
This is the same for everything.
Oh, okay.
This is actually the same as this, right? Because our force here is mg, and our distance is height.
Oh yeah.
So this is, the work thing works for everything.
Yeah.
But this one only works for gravity.
Gravity, then okay.
If you're lifting against gravity, it's mgh.
Okay.
But every situation will be F. Okay, is there another one? Okay, that's it for potential energy. Let me stop the video.